Swayam Prabha. Digital India. Educated India.
In the last lecture, we were discussing the various design parameters for the border irrigation system, and I had given you this equation for this was the equation which we had written for the unit rate of application or the unit stream size, and I had used an efficiency which I had called application efficiency. The way we have defined our application efficiency, if we recall, we are defining the application efficiency as two components. One is the application efficiency and the other is the distribution pattern efficiency. So in our case, because there is a lot of overlap in these areas, we had defined an application efficiency which was volume delivered to the application surface to the volume of water delivered to application device. That is how we had defined our application efficiency. Do you remember that? And along with this, we had defined another efficiency, though this is multiplied by 100. There is another efficiency which was the distribution pattern efficiency. So ED we were calling as distribution pattern efficiency, and that was volume of water stored and root zone to the volume and delivered to application surface. That was what the combination of these two we said will give you the application efficiency as is normally defined, isn't it? So in this, we will rather than using just EA, we can either say is a combination of EA and ED, but specifically in this particular situation is assumed that EA as defined here, EA is 100%. That means there is no loss when you are supplying the water from the device onto the application surface. So, we are assuming that there is no loss in real application, because this is a generic purpose definition which is also used in the context of sprinkler system, where you might be losing some water when the water comes out of the sprinkler head or the sprinkler nozzle and is applied onto the surface of the field, the application surface. But in this particular situation, when you are using the irrigation methods, you might find that this can be easily taken as 100%. Okay? So, your application efficiency is basically confined to the ED value. So, instead of using EA as we had used in the last class, I think we will better either use the combination of these two, or if we assume that EA is 100% as per this definition, we will just use ED, which will give you the distribution pattern efficiency, which will give you an idea that how much of the water is actually stored in the root zone in comparison to what has been delivered. Okay? So, this efficiency ED, what is the level of efficiency which should be used when you are designing a system? You have to have some available values from the experimentation, from the actual data available, and that is available in the form of some tables, and one such table is available, which I will make available to you during the course of your the notes or the sport material which I am preparing for you. But I will just to give you the suggested design application efficiency, or the design distribution that the pattern efficiency which we have just defined. This ED value is given for different intake families, and we had discussed what the intake families are. So, for different intake families, there are relationships available where you have for different slopes, and the slopes are given in meters per meter. For different slopes and for different intake families, let us say that these are the ranges of the intake families, which will in turn suggest what is the type of soil which you are using. So, intake family will be basically this value is a function of what type of soil you are using, and it will also depend on, along with the intake family, how much is the depth of application. Okay. And the depths of application, these are the various possible depths which are frequently in use. 25 millimeters, this will be in millimeters, 25 millimeters, 50 millimeters, 70 millimeters, 100 millimeters. In some cases, you might have 125 millimeters also. These are the most common depths which are prevalent in actual use. So, dependent on what is the intake family, what is the value of the slope variation, again there are different prevailing slopes which might be the range can be quite large and so on. You might go up to around 6%. The 6%, and here we are using it in meters per meter. So, in terms of percentage, this will be 6%, this will be 0.05%. For these slopes, for a specific value of the depth of application and for a specific value of the intake family, there are some recommended efficiencies, which are the design efficiencies, which are achievable efficiencies. Those efficiencies can be used to find out the unit stream size. I'll give you an idea about for the case of a family of 1.5 and for the values of depth of application of this range. Just to give you an idea what can be the possible variations of these efficiencies. For the slope is again 75, 75, 80%, 80%, 80%. Let's look at the last slope here, 50%, 55%, 50%. So, this is the variation. I have just picked up some values from the recommended values of the table. You will find that let's have some values in this category also for 0.3 intake family. What is the order of magnitude of these? You will find that in general, when the slopes are flatter, you can get the higher values of efficiencies. When the slopes increase, in some cases, it might not be feasible anymore to have under a specific intake family. You might not be able to use a slope beyond that specific slope. For example, in this case, the value of 50% efficiency is achievable when you have a slope of 0.5% and the depth to be applied is 25 millimeters. Okay. You might not be able to get an efficiency which is even 50% if you try to apply a depth which is more than 25 millimeters with such a slope and with such a family of the soil. So, there are some recommended efficiencies or the efficiencies which have been seen to be achievable through the experimentation. Those values have been recommended here. You can use them for your design purpose. Okay. But in general, you will find that the higher efficiencies can be achieved for moderate soils which have moderate intake. Even the higher values of these intake family numbers will suggest that the efficiencies will lower down. But in this range, somewhere from 1.5 to 3 intake families, you will have quite reasonably good intake and the efficiencies which are achieved. But as you increase the slope, there will be deterioration of those achievable efficiencies. Okay. So, having selected an appropriate value of ED, you can substitute that in the value of the relationship of the unit stream size and get a value which can be used for your specific conditions. Suppose you have found out the unit discharge, you have adopted some value of the length of the border. You have also picked up the values like how much depth of irrigation is required. That is again known, that is a function of what is the requirement from your crops. The design will also involve in checking these parameters, checking these values, whether these values are within the permissible range. So you should also look at the design limitations, and these limitations are in the form of checks. So once you have come out with a design, once you have selected some parameters, you must check those parameters with respect to the various criteria, and these checks are in the form of, you can check the inflow rates, you can check the depth of flow, or the border slope, remember I had mentioned that there can be different possibilities. You might have some things which are fixed in your conditions. So you can check those items whether they are within the restricted ranges or they are not within the restricted ranges. Once you have checked those things and you have satisfied your design parameters, basically what you are checking for is one major thing is that you shouldn't have any erosion problems. They are very detrimental for your total irrigation process. And there are some other conditions which we will see subsequently as we go further. So let's try to look at these items. Let's try to check our designs. Let's try to look into the relationships which are available for these checks which we have just looked at. One is the maximum flow rate. In some cases, these relationships are based on the hydraulic equations. In some cases, there are some empirical relationships also which are put forward, and they have been obtained from the actual experimentation. So to find out what is the maximum unit rate which is permissible, and this is basically from the point of view of the non-erosive nature of this stream. What is the stream size under the specific conditions which can remain non-erosive? That is what we are trying to look at. Because the stream size which you have found out, you can check that stream size against this. And this relationship is given for under two conditions. This is basically, we are trying to look at from the point of view of non-erosive. And the two conditions are in terms of what type of crops you are having. The first variety of crops are those crops which are non-sod forming crops, which include the crops like alfalfa or small grain crops, which are not having a lot of resistance. Their root system is not very well formed. So all those crops, if you encounter those crops, then your maximum unit stream size is given by this relationship. Where S naught is the slope in meters per meter. So, S naught is the slope in meters per meter. And the second case is the case when you have well established dense sod crops. So, in that situation, the erosiveness of the stream size won't affect the field to that extent. So, you can afford to use a maximum stream size which is higher than the previous one, and the relationship which is recommended is similar to the previous one. So, it's almost, you can see here that is almost double than the previous, because we had used a coefficient of 1.765 in the previous case. Here we are using a coefficient of 3.53. And this QU you are getting as in meter square per second. Okay. The order of magnitudes, the maximum flow rate, which we have just written the two equations for two different cases with respect to the crop type. We have said that in one case we have normal cover, and the other case is the dense cover. The non-sod type is the sod type, and for the slope, let's have a look at some values. Maybe if this is the slope 0.05%, you can afford to use a stream size. Now, this stream size is not in meter square per second, this is in liters per second per meter width of the border. Okay, the units are different. So, you can use a 52.8 liters per second per meter width of the border when you have such a flat slope. But if the dense cover is there, you can still use a higher stream size. If the slope is 0.5%, then it reduces to 9.3, and this will be around 18.8 or so. Similarly, let's say that if this is 4%, you might not be able to use a very high stream size. This will be as low as 1.97. So, you have to look at what are the prevailing conditions, and the other parameters will have to be decided by those conditions. Similarly, the when you look at the depth of flow, in general, the depth of flow will be a function of how much is the ridge, what is the ridge size you have. Because when you are constructing the borders, you will have to enclose it with the ridges. All these borders which you are considering so far, we are not looking at the length in that manner. We are assuming that we can use the borders in two manners. One, you can have open-ended borders where you don't have the ridge at the downstream end. So the border is not blocked. We'll come to that later stage, at a later stage, where we can see that how we can look at those borders where you have the end blocks in place, in position. Because in the case of borders without any end blocks, you might have some surface runoff. Some runoff can take place. So that runoff, if you want to avoid, you can use the borders with the end blocks. Now when you are looking at the maximum depth of flow, the depth of flow, let's say at the head end, it should not exceed the height of a ridge and you cannot allow the water depth to get accumulated up to the height of the ridge, because once the ridge is overtoppled, it might get washed away. So you have to keep some freeboard. It shouldn't exceed the height of the ridge minus some freeboard, and this freeboard is normally around 25% of the ridge height. That is the general criteria which is used, that 1/4 of the ridge height you keep it as freeboard. So your maximum depth should be basically around 3/4 of the ridge height. In terms of the actual quantities, the value which is normally used is around 150 millimeters. The depth doesn't exceed around 150 millimeters in most of the cases. But in some cases, if you have a soil which doesn't have much erosion problems, then you might use some value which is approaching around 200 millimeters. This is to be used only in those cases where you have non-erosive soils. The soils are not as erosive as in the cases where you are using a smaller depth. But the recommended depth is around 150 millimeters. These were the approximate ranges, but you can also find out, you have the relationships which can give you the depth of flow, the maximum depth of flow at the upstream end. And there are two cases which have been considered. We have already seen that the gradient of the border will make a lot of difference in terms of what is the normal depth which is getting established, and we had said that if the slope is more than 0.4%, then we'll call it as the high gradient border, otherwise we'll call it a low gradient border. So if you have high gradient border, then you will achieve at the upstream end, you will achieve a normal depth, and that normal depth you can find out using this relationship. And this relationship, all these quantities we have already defined, the units are all same. This is in meters square per second, and the dn which you are getting, this is in millimeters. Okay. And for the other case, when you have low gradient, border, now in this case you might not be able to achieve the normal depth. The depth at the upstream end is given by this relationship. So this is the case when the slope is less than equal to 0.4%. Now you can find out the actual D, and then you can see whether is it within the permissible range or not. Okay, and you can also see whether your the ridges which you have provided, will they be able to take care of the depths which will get accumulated with respect to the other variables, because this will be now dependent on what is the TL, what is QU, and the N value. That was the maximum depth of flow. Let's look at the minimum stream size. What minimum stream size you can afford to use? This is a condition which is the other extreme. You are using you are trying to find out the maximum possible stream size with the condition that there shouldn't be any erosion. Whereas in most of the cases you might find that is not the maximum is constrained by the other restrictions, the availability, what stream size is being made available to the farmer. So he might not be able to achieve the maximum stream size which we are talking about. But minimum is more important from his consideration, because minimum stream size is achievable. He might have the control to apply a stream size or use a stream size which is as low as possible. But at the same time, he must know what is the minimum stream size which is practicable, which is suitable. So that has to be seen from the angle of what is what will give a sufficient spread, what stream size can give a sufficient spread over the border length. So from that angle, the minimum stream size, this must be sufficient to spread over the entire border strip. Okay. The minimum stream size, if we designate it as QU minimum, this is given as into L into S naught by N. So you can check your minimum stream size whether it is below this. If it is below this, then you will have to revise that minimum stream size, because that will give you a very low efficiency which won't be acceptable. So this is another check which you must apply on your design parameters on the stream size which you have computed from the previous expression. Now let's talk in terms of the other important parameters, which is the slope. If you want to change the slope, the prevailing slope, that is a parameter in your hand. You might, if you are forming your areas, if you want to relay your areas, you might like to change the existing slope to another slope. So in that case, you can even think of providing a slope. Now what slope should be provided? What slope is a reasonable slope? That is what you have to know the limits. What is the maximum slope? So if that is the situation where you are interested in knowing what is the maximum possible slope which can be used, you can use this relationship. Into okay. So all these terms, the Tn is the net time and this is the lag time, which we have already seen in the previous class we had explained. So this is basically the application time. Tn minus TL is the time of application which will be required, and Yn is the depth. Ed we have seen as the distribution pattern efficiency, and N is the Manning's coefficient. Normally the slope, any slope which is more than 4% should be avoided. So if you get a slope which is more than this, it should be restricted below this. But in general, you can, for the prevailing conditions, you can find out what is the maximum possible slope which can be used, and you can check your slope against that. Let's come to the border length. The maximum border length this is usually limited by the maximum unit inflow rate. But again, it depends which slopes you are using. If you are using steep slopes, then the non-erosive stream size has to be the limiting factor. And if you are using the flatter slopes, then the maximum depth of flow will be the governing criteria. But the maximum length, you can use this expression to find out the maximum length. This is basically the same equation which you had used in the beginning. So you can find out for the maximum possible stream size what is the maximum possible length. And in some situations, if your intake rates are very low, you might find that you get a very big value. In general, any length which is greater than 400 meters should be avoided. Okay. So the length in general shouldn't go beyond 400 meters, it will become unmanageable. In all these situations, one more thing that we are using, at every place we are using ED. But in case you find that the EA is not 100%, if you are certain that EA is some value which is less than 100%, then you must use, along with ED, you must use EA also. Okay, that is very essential, unless you are certain that EA is close to 100%. So you can improve upon all these relationships wherever you have used ED, you can substitute EA into ED if EA is not if it is not known to be 100%. If it is less than, if it can be seen that yes, it might be less than that, so you can use the actual value. Let's consider the cases where you want to use the borders with no runoff. That means you are using the end blocks you are trying to restrict, if there is any surface runoff, you are trying to restrict that surface runoff by putting a blockage at the end or by constructing another ridge at the end. Now then, when that happens, basically let's first look into that why you should think of that, because any surface runoff which is taking place is going as a waste. So it's reducing your overall efficiencies, and you can think of using this surface runoff in some manner. There are two possible options available. What those two possible options are, the first option is that extend the border length to impound to impound the runoff onto this extended length. So all that surface runoff which was taking place earlier, if you find out how much length of the border has to be extended to accommodate that additional runoff which was available, so you can afford to extend your border length and consume this surface runoff in that extended border length. That's one way of handling this problem. The second possible manner can be to reduce the stream size. So in the second case, you can reduce inflow rate in this case. You have not changed the length of the border, is the same as the original length, but in turn you have reduced the inflow rate to such an extent that there won't be any surface runoff. Fine. Let's look at the first case. And the first case, when you are extending the border, when you think of extending the border, the length up to which the border can be extended is limited to the lesser of the following two conditions. Condition A is in this condition, what we are saying is that the length covered by an impoundment whose maximum depth is equal to the net infiltration depth. What we are saying is that the equivalent length, or the length which has to be increased, in that case will be equal to yn by, basically what we are saying is that if there is the slope, this is the slope of the area. If we know what is the yn, up to which length will be the equivalent length up to which it can be absorbed. So this is a very simple formulation, and yn is the units which are used. Yn is in millimeters, L is in meters, and S naught is in meter per meter. Now this is one condition, and the second condition is that length which can be adequately irrigated by the volume of runoff from open-ended borders. What we are checking is that what we are interested that any extended length which we are trying to make use of, it should have sufficient depth and it should also be in a position to take care of this requirement which is in this extended length properly. So that from that angle, from the requirement point of view, this extended length is given in this form into the original length. Otherwise, there is no point if you try to extend the length without looking at what is the requirement, what is the chances of getting this length chances of getting this length satisfy its own requirement. There is no point in extending. So that is what we are trying to look at, both the conditions. One, there should be sufficient length, and second, that length, whether is it taking care of its own requirement or not. If it is not taking care of its requirement, then we will reduce the length to that limit where it can take care of its requirement. So we are, out of the two conditions, we are choosing the minimum, and only that much length is extended. In this equation, ED is same as before, the efficiency, but RI is the factor for effect of intake family, so there is a factor which is dependent on the intake family, and that takes care of the effect of the intake family on the runoff, and Rn is another factor which is dependent on the roughness of the area. So this factor is used for the effect of roughness on runoff, and L is the original length of the border. Now there are values which are made available for different intake families. For different intake families, RI is as given. I can give you the values. This is 0.9, 0.8, 1.0, 1.5, 2.0, 3.0, 4.0. These are the factors which are recommended factors for different intake families, and similarly the other is between Manning's N and the Rn value. these are the values for recommended for different Mannings N. So, the impact of different roughness and the intake families have been taken care of, and finding out what will be the equivalent length, or what will be the length which can be extended to account for that surface runoff which is being produced. I think we'll stop here. I can take on any questions if they're there.